Okay, so let me first apologize to many of you who have heard one version or the other of this talk. But Tom sort of wanted me to give a review kind of talk about this subject, so maybe it's slightly different. Let's see. So this is, I think the better topic actually, the better title would be something like Beyond the Kinetic Limit or Beyond the Weak Coupling Limit. So let me let me slowly get into that, but to go to the background, I mean that's the problem which of course many of us would like to understand, namely how to starting from completely completely time reversible dynamics Hamiltonian system, for example Hamiltonian system, to derive dissipative dynamics. So from a system which has conserved quantities like energy or momentum or both, and whose microscopic dynamics is time reversal invariant, nevertheless you would like to show show that when you look at macroscopic quantities you will get dissipative dynamics. So I will come back to this kind of picture late in the very end only, and what I will discuss most of the time is related a slightly simpler case where you, instead of having looking at this locally conserved quantities where they're diffusion, look at this problem, the classical problem of Brownian motion, namely a particle interacting with an environment, again a Hamiltonian system where but you instead of looking at the whole system you look at a part of it, and in such a case again in the normal situation you would like to show that the motion of that particle is in the long time limit in long times behaves diffusively. Okay, so let's look at a couple of models for that. I will go through a couple of models and then discuss sort of an approach which is sort of trying to catch such models. So a classical model of just of the kind which I have here would be just this particle is interacting with the other particles with some potential, and in the simplest case the other particles don't interact with each other, so they form an ideal gas. So you have a Hamiltonian for the particle, the blue one, and then for the gas, and the potential which is between the position of the particle and the gas particles. And then let me put a coupling constant in front of here, so that will be something which will be important later. So again you have a Hamiltonian dynamics for the full system, time reversible dynamics for the full system, and of course if everybody here well knows one particular limit of this is where the gas particles are taken infinitely heavy and they don't move. That's the Lorentz gas. So the motion is again the same. Only the motion of the gas particles is removed. They don't move, and you have such a Hamiltonian. Quantum version of the both of these models are, of course, also well known, hopefully, to everybody. So let me, for convenience, look at the quantum case actually on a lattice. So you have a particle which is hopping on the lattice, and so this is the Rayleigh gas version of the lattice, and interacting with some again a free system, and this time let me take it the free bosonic field on the lattice, or in the continuum, but the particle is moving on the lattice. And Hamiltonian is again the same, so now it's quantum mechanics, so the p squared is Laplacian. There is the Hamiltonian of the free field, and then there is an interaction which is taking place again, so that you have a potential which where the particle feels the field nearby itself. So take a short range potential here, v, and then phi is the field, and in the simplest case just couple it linearly, so the Hamiltonian interaction is linear in the field. Okay. The Lorentz-Gas version of this is the Anderson model, and one example where you take just the regular one, which everybody knows. You replace this coupling here by just random potential. And the equation of motion for the density matrix is the usual Schrödinger equation. Okay, so what would you like to show? So you should, in the classical case, you could, the simplest version of trying to prove diffusion is just look at the expected value of the particle position squared at time t, where expected value is in the Lorentz gas, just you take average over the positions of the scatterers. In the Rayleigh gas, you take average over initial conditions of the gas. So you take an initial state for the gas and compute with those initial conditions, random initial conditions, and then take average. You could try to prove more, almost sure convergence to Brownian motion invariance principle or whatever. Jörg.
I don't understand that. You would have to rescale something, because in all these models, the velocity is a good variable.
Yes, I will come to that.
Perfectly finite.
Right, but I will come.
Energy.
Yeah, but I will come to that. But I mean, the motion of the particle in the end will be diffusive. The velocity will, in these models, the velocity will basically become a stationary process, and then the position will be diffusive.
You're on the lattice. That's
In the quantum case, I would be on the lattice here. Okay. In the quantum case, of course, it would go the same way. So you take instead of expected value of q squared, you take the trace of the density matrix times q squared first of all, and in the Anderson model, then you would take average over the random potential. In the Rayleigh gas, you take an initial thermal state for the free field, and that's included in this trace here. So there's the randomness comes in the slightly different in the two cases. Okay, so what do you expect in these cases? I had in every case I had this lambda in front of the potential. So in the classical case, where am I here? So for small lambda in all these models, what you actually do is you expect in the cases where there is diffusion, you expect this diffusion to be happening on the scale 1 over lambda squared. So another way to say is that there is a scaling limit for these models, so that if you take this lambda to 0 and simultaneously scale space and time by 1 over lambda squared, then the motion actually becomes Markovian. So let me explain this a little bit more. So in the Lorentz gas, as Jörg just said, what happens is that the velocity becomes a Brownian motion. So if you look at the Lorentz gas, then what the particle is doing, because the interaction strength is lambda, it's in time t, it's feeling t random scatterings where the velocity changes of the order of lambda. So you expect that in time lambda squared, 1 over lambda squared, the velocity becomes random, and of course the total velocity in this case by conservation of energy the total speed doesn't change. So what you expect in that time scale is that the velocity becomes Brownian motion on the constant on the sphere of constant velocity sphere, and then a particle position, then whatever comes from such a velocity. And this is of course proven a long time ago by various people. So for Kesten and Papanikolaou, and then due to Goldstein and Leibowitz. Now, in the Anderson model, the similar statement is that you look at the density matrix at time in units of 1 over lambda squared, and look at it around the diagonal in the following way. So you scale the center of mass by 1 over lambda squared, and then take the limit as lambda goes to 0. Then it was proven, and actually stronger statement just than what I'm saying here, was proven by Erdős and Yao, namely that in that limit, the limit object satisfies a linear Boltzmann equation, and now if you study the long-time dynamics of that equation, namely this variable here, this capital X, or the quantum version of that, then that will be diffusive. Okay, so of course in all these models there are other Markovian. For the gases, for instance, you can look at small density, large mass, etc., similar statements. But what we would really want to do is not to do this, namely take the interaction to 0 and look at timescales longer and longer. This, of course, amounts to proving diffusive behavior up to certain times, namely times longer and longer, the smaller the coupling constant is. What we would rather want to do that we keep the lambda fixed and take t to infinity and prove diffusion there. Of course, we know that sometimes these limits don't commute. For instance, in two-dimensional Anderson model, where weak coupling limit is diffusive, nevertheless, if you go to much longer time scales, you expect localization to enter much longer time scales of the order of 1 over exponential in the small parameter, in the large parameter. For fixed systems, so keeping sort of the system fixed and taking time to infinity, there are very few results, as you surely know. There is, of course, the classic result by Bunimowicz and Sinai on periodic Lorentz gas, where they proved diffusion. In Rayleigh gas, only one dimension in terms of upper and lower bounds was done also a long time ago. Now, if you take Anderson model where the potential is not this frozen random potential but time dependent and Markovian, then actually you can prove diffusion. And that's what Kang and Schenker did recently. In 3D Anderson model, one can go beyond this kinetic time scale, so improve it by an inverse power of lambda. That was done by Erdős, Samhofer, and Yao. And then, of course, there is, in a related model, actually diffusive behavior proven by Disertori, Spencer, and Zimbauer. What I want to describe here is a model where one can go beyond this kinetic scale and actually for fixed lambda prove diffusion, and that was introduced by Wojtek, De Rock, and Jürg some time ago, and studied by them and by Wojtek and me. Okay, so that's, before I go to that, let me try to explain a little bit what the idea of Wojtek and me is in this kind of situation. In general, that means illustrating the Anderson model. So in the Anderson model, of course, I'm not claiming any result whatsoever, but since it's familiar to everybody, let me try to illustrate what we are trying to do in that. So let's take the Anderson model, so minus Laplacian plus lambda v, and you are supposed to study the time evolution of the density matrix. So let me call the dynamics by L, the commutation with Hamiltonian. So what is the kinetic limit? So we have this unitary evolution, and given by you go in time 1 over lambda squared times some fixed parameter tau, and then you do the scaling, which I showed before here. So you scale the center of mass coordinate. So you still have a unitary unitary operator, which is of course a random unitary operator because L is a random by V. And let me call the average of that operator, let me call it T. So that is measured in units of the kinetic time scale. So I call it tau. So tau measures in units of 1 over lambda squared. And it depends explicitly, it depends implicitly on lambda, because lambda is in the parameter both in the scaling and inside the Hamiltonian. Okay? So weak coupling limit states that this random operator, this non-random operator, this operator here has a limit as lambda goes to 0 for fixed tau. And the limit is a Markovian semigroup. So it's exponential of tau times a Markov generator. And moreover, this is a semigroup which diffuses. So namely, if you now, after you have taken that limit, look at the long tau limit of this, so do the usual diffusive scaling, you get something fixed, some diffusive behavior. Now, we are not interested in, we would be interested in actually taking the tau to infinity here, so not lambda to 0, but tau to infinity and lambda fixed. Okay, so so we would be interested in, for instance, the diffusion constant, where you take this operator here, average it, take the trace q squared, and then take tau to infinity. If you go back to the original scale, then there is 1 over lambda squared in front of the diffusion constant. So the diffusion constant is 1 over lambda squared times whatever this limit is. And more generally, you would like to show that under diffusive scaling, so if you take this operator, the average of the unitary chi, and scale it diffusively, you go to something which looks like, at least on diagonal density matrices, it looks like ordinary heat kernel with some diffusion constant kappa. So writing things this way, what Erdős, Samhofer, and Yao proved is that you take this guy, you are still taking lambda to 0, but you are taking the tau here also to infinity with lambda slightly, with some power of lambda. So what they showed is that you do this thing, but not with lambda fixed and tau to infinity, but lambda going to 0 and tau going infinity at the same time. Okay, so their limit is still the same as in the weak coupling limit here. Okay, how would you try to go beyond this? Okay, well, if I fix lambda, then it's clear that the Markov property fails here. So I remind you that this t here was the expectation over the randomness of this unitary time evolution in the kinetic time scale. And that's, of course, a group. It's not only a semigroup, but it's a group. So you can multiply them. But the expected value, of course, doesn't commute. So this guy is not only in the limit as lambda goes to 0, is this thing a semigroup, but not for finite lambda. So what you could try to do is to say that, okay, well, let's write it. If I look at just time 1 in the kinetic time scale, let me take average of it. So call that, as I'm calling t, let me drop all these indices and call it just t. Let's call it u. And then look at the fluctuation, which is u minus its average. Okay, so that way I can write the unitary evolution as this sort of diffusive evolution plus correction. The correction is just the correction. And to understand the long time limit of the original problem is the same thing as to understand the long time limit of this u, namely the long time limit of this t plus b. So I just want to take the tauth power of this guy and look at what happens to it as tau goes to infinity. So this way of writing it, we could think about u as a random transition kernel, t is its average, and b is a fluctuation. And this way writing the fluctuation has 0 average. And then we are iterating this random transition kernel. So this is, of course, sort of reminds a classical problem of random walk in random environment. The transition kernel T was exponential of a Markovian generator. So if I didn't have this guy, I would just have a random walk or quantum version of it. And then the B spoils things so that you have something which depends on the randomness and also is non-Markovian. Okay, so since we know that this guy has a limit as lambda goes to 0, that's the weak coupling limit, then we expect that this T here and is a diffusion, and actually it is. I mean, this was proven by Somhofer, by Ederson Yao. This is a diffusive Markov chain, so T is more or less whatever the weak coupling limit and a small correction. And the B is something. It's a random environment for it. And what we want to study now is the long time limit of this and diffusively scaled. So what I want to, the way I want to study this long time limit is to study it sort of step by step, not going immediately to the time going to infinity, but to do it fixed, going from one scale to the next and always do the rescaling. So this is what we want to study. So I'm looking at, I'm just replacing the time by some powers of a fixed parameter L, fixed integer, and looking at the original time evolution rescaled by diffusively rescaled with index n. So the diffusion statement is that this expected value of this guy goes to some fixed point, which is a diffusive fixed point. This is what we would like to show. Well, we could study it in here. I'm writing it that I'm taking n to infinity, but of course there is a clear semigroup structure here. I'm taking powers of n here in both cases, so I can do it step by step. Namely, if I've done it up to time scale L to 2n, I can go to the next one just by iterating this thing one time. So I solve a problem where I've sort of constructed the expected time evolution at scale n and some fluctuation. I go with that evolution time L squared and rescale by space by L. So this is a finite, take L order unity, so this is a finite time problem. So this is an iteration where if I take expected value, I get the new average annealed time evolution. And of course, to control this, I should know something about the noise here. This single scale step is something which you can, of course, perturbatively try to study if you have succeeded showing that this is a small perturbation here. So the new guy should be just the rescaling of the diffusive rescaling of the old guy and expected value of some correlation functions of the noise. And the new noise would be some linear transformation applied to the old noise plus hopefully something small. So that's what you would like to show. Now, if you could show that the moments of this randomness here go to 0 in sufficiently strong way so that this really is a small contribution to that, then you would be in business in trying to show actually the diffusive limit. Stated in another way, if the noise is irrelevant in this renormalization group transformation which I've sketched here, then you have a diffusive limit. Now in Anderson model, this is of course hard, as you can imagine. The noise here is very complicated, and in some sense it should be small, and once you do the diffusive scaling, you expect it to be in some sense go to 0, but certainly this is something which I'm not claiming to be able to show. but there is a modification of the Rayleigh-Gas model. So this goes at least back to Jürgen and Wojtek, where actually this kind of ideology can be carried through. So that's what I will describe now to you. So let me go now to the Rayleigh gas. So quantum case, so the quantum particle. Let's add a spin to it. So, for instance, two-component spin. So, particle hops on the lattice, and then it has also a spin. So the Hamiltonian is like before, except that there is also the spin Hamiltonian. You could take the spin Hamiltonian, for instance, just Pauli matrix in third direction. And then there's the particle, then there's the, let me call capital E is the environment, so the free field. Free field is given by, in terms of creation and annihilation operators and some dispersion relation omega. I will come back to this omega in a moment, but here what the Hamiltonian formally looks like. And then there is the coupling of the particle with some potential to the field at lattice sites. Okay, so Q is the position of the particle. That's the free field. And the coupling is short range, so the particle feels the field mostly where it is. And it's also a matrix in the spin. You could take this, for instance, the Pauli matrix sigma 1 times some short range potential, okay, as an example. And the only twist, what compared to this is more or less a Rayleigh gas, except there is one little degree of freedom, or what I call the quantum Rayleigh gas. But what we will do here is we will take the particle very heavy. So there is this parameter lambda, and the particle will be taken very massive. So the mass of the particle will be 1 over lambda squared. Lambda is going to be fixed and small, but compared to the usual Rayleigh gas model, where m is order 1, I would take it like that. I will scale time in a second, so if you wait for the next slide. But before I do that, let me first explain what the states are. So you start with an initial state, so the particle, for instance, take it a product state of the particle and the environment, and take the particle, say, located at the origin and whatever in the spin. Okay. So the density matrix is just at the origin, and for the environment, free field, it's natural to take the equilibrium Gibbs state with temperature, inverse temperature beta. So given formally by this formula here. Now the dynamics of the full system, where rho is the density matrix of the system and the particle, is given by the same formula as always. So the full density matrix, the initial density matrix, evolved by the full Hamiltonian of the system. And if you look at the particle itself, with what we want to do, then we trace over the environment. So I look at the reduced dynamics for the particle. So take the full density matrix of the system plus environment, trace it over the environment. So concretely, that's the initial state. You evolve it in time t and trace over environment. Let me call this operation here. This is a linear map from density matrix of the particle to a new density matrix of the particle. It's a linear map, and it's the analog of what we did in the Anderson model, where we took expectation value over the scatterers. So here, let me call that operator. This is the expected value of the full exponential of the Liouvillean of the whole universe, expected value over the environment. Okay. So this is a notation. It's, of course, this is a quantum thing. It's non-commutative. It's not exactly probabilistic expectation, but it has many such properties, so it's useful to call it like that. So this plays the role of the expected expectation in Anderson model. Now, if I had a Rayleigh gas, then the weak coupling limit, so if the mass would be order 1, it would be the same story as in the Anderson model. So you would take the average like this in time in units of 1 over lambda squared and rescale space by lambda minus 2. And the limit would be again a diffusive Markov semigroup. And this was actually proved by Latzi. When? Some time ago. Okay. Now, so if M is order 1, and you want to keep the lambda non-zero, then this is at least as difficult as the Anderson model. So again, you could set up the renormalization group like I did, but I wouldn't have much to say about that. Whereas in our model, things.
There would be a difference, right? I mean, let's go back to that previous slide. They may have some similar technical difficulties, but the phenomenology would be different.
Phenomenology would be different, of course. In the Anderson model, you don't diffuse in the energy. You diffuse in energy only.
Not see localization in this model, right?
Also localization, yes. But if I'm talking about the like 3 dimensions, the diffusive here energy is also diffusing on. In Anderson model, energy diffuses in time scales much longer than the usual diffusion. But you're right. I mean, in low dimensions, you shouldn't expect to see localization here. So you might say that maybe it's easier. Okay, so now we are taking mass of the order of 1 over lambda squared. So things are now simpler. So instead of here where the mass was order 1, we had to do the spatial scaling. Not only go to time order lambda squared, but also 1 over lambda squared, but also scale space by 1 over lambda squared. Here, if you take mass of order 1 over lambda squared, the particle during that time 1 over lambda squared doesn't move more than order unity. But the spin, of course, if I look at the Hamiltonian, the spin has nothing here. So the spin feels the interaction just like in the like always. So it's a long time. So the spin and also the momentum of the particle thermalized during that time. So if you want to study the weak coupling limit of this model, you would only look at times of the order, just like in the Anderson model, times order 1 over lambda squared, but you wouldn't scale in space. Okay, so if I have again this expected value, so trace over the environment of the Liouvillean in time tau over lambda squared, then this guy has a limit again as lambda goes to 0, but this is a very different Markov process from the one which Latzi constructed here. Namely, this is basically a process where the particle is moving, jumping order unity. So at this tau time scale, it's making hops of order unity and with random directions in spin and moving randomly in the spin and the direction of the velocity. So now this Markov process is again diffusive. So if I now study what happens to the particle, what happens to this in this motion when tau goes to infinity, you again have diffusion, but for the original model, the diffusion constant is very different from Anderson model because the lack of the spatial scaling here. In Anderson model, we had order 1 over lambda squared. The diffusion constant here is order lambda squared. So this suggests that this should be much easier to analyze. And indeed it is. And let me explain you how that goes with this renormalization. So what am I supposed to do? I'm supposed to fix lambda and study the long-time asymptotics. So to remind you what we were doing, we have this. Let me look at just one timescale 1 in the kinetic timescale. So I look at time 1 over lambda squared unitary evolution, time 1 over lambda squared, and I split it into two, namely its expectation, the trace over the environment of this operator, plus then the fluctuation. And now I'm supposed to look at this in longer time scales, so in units of the kinetic time scale. So I want, and let me take them exponentially. So I go from scale to scale, L to 2n divided by lambda squared, and simultaneously rescale diffusively. So I have at time scale L to 2n times the kinetic scale, I have unitary evolution rescaled by the usual diffusive rescaling in space. Let me call that un. So what we want to show is that this goes to a fixed point, the average of this u. And actually we want to show that the u goes to a fixed point in the sense that even if it's a unitary operator in the limit as n goes to infinity, this random part here will disappear, and all what I'm left with is this diffusive fixed point T star. Okay, so as I said, it's instead of looking at this immediately, it's easier to look at it iteratively. So you go from timescale n to timescale n plus 1, where you just have to solve a fixed time problem with a renormalized average and renormalized noise. And what you want to show is that this renormalized noise goes to 0 in suitable sense as n goes to infinity, so that you can control the annealed part, the Tn. Now, as I said, this is a random walk in random environment. This is a Markovian random walk, and this is something random and also non-Markovian correction to the random walk. So you would to show that a random walk is diffusive in a random environment depends on the correlation structure of the environment. I mean, our environment is sort of produced by the interaction of the particle with the field. So it's and it's slightly subtle here because the particle is, of course, the field is influencing the particle, but the particle is also influencing the field. So the environment is not Markovian. So the walk is not Markovian either. There's there's a lot of memory there, and it's random in this quantum sense as a function of the environment initial state variables. Now, but it's really produced by the field, so you should expect it to, whatever correlations it has, they are inherited from the free field correlations, and that's of course a simple thing to study. So the free field has of course explicit correlation function, and what kind of decay it has in space and time depends on what this dispersion relation here is. But typically the cases you are interested in, it has polynomial decay in time. So if I look at the 2-point function of the free field and look at it fixed in x and look at its behavior in time, then it goes like 1 over time to power some power, and that power depends on the small momentum behavior of the dispersion relation. So when omega goes to constant for k equals 0, then you get decay like t to power minus d over 2, and when it goes to when it's absolute value of k, when k goes to 0, then you get weaker decay. So photons, for instance, are in this decay. So you see that in 3 dimension, this decay is integrable. In 2 dimension, it's not. And this decay is integrable in 4 dimension, but not in 3 dimension. Turns out that that's important for us. But let me first state the result before I state why it's important. So if I take this a bigger than 1, so if I take the decay, correlation decay integrable in time, so that means in 3 dimensions that you take this, not the photons, but the ones, the massive photons, if you wish. Then the particle motion is diffusive. Namely, if you look at the particle position at time t and take t to infinity, then it goes diffusively with diffusion constant, which is lambda squared times the diffusion constant of this Markovian semigroup plus a correction. So this such result with different method was proven by Jürg and Wojtek in dimension 4 and with some assumptions on this omega. Now, how would you, I told you that this depends, the random environment, the decay of the random environment is important for the whether a random walking random environment is diffusive or not. So let me try to get into that, how that goes. But before, how would you actually start studying this noise correlation function? So this was the field correlation function, but we are interested in the noise correlation, the B, the correction to this Markovian evolution. So how would you get into that? Well, I mean, that's what we are trying to take an average over. So we have the full Liouvillean, full unitary evolution, which has the particle, the environment, and the interaction. If I didn't have an interaction, things would be simple. So let me expand this in powers of interaction. That's the way you prove the weak coupling limit, is by expanding that. So let's expand it in powers of the interaction. So I'm looking at this in the kinetic timescale annealed operator, so the trace of this. I expand it in powers of interaction. That's the usual Dyson expansion. So it's in powers of interaction and some free evolutions in between. And you want to go in timescale of order 1 over lambda squared. And and what you see is what is occurring here is basically the interaction computed at various times between the final time and the initial time. And the field is a Gaussian field. The correlation functions are gotten by it's a free field, so the correlation functions are pairings of this. Remember that this is linear in the field, so the correlation functions are just pairings between these LIs. And the pairings of the LIs, well, since it was the field there, it's just this correlation function which I wrote to you, the field correlation function. So you have some sort of graphs in time, pairings where the pairings decay polynomially in time. So it's obvious that to control this integrals over time, some decay is needed here. So that's the annealed dynamics.
So there are presumably oscillations in there too, which you don't.
Of course, there are oscillations. Yes. So now this expansion converges. If I fix time here, it always converges. But the useful bounds you can get only for this kinetic timescale or the unity. So I told you already that if I keep the kinetic timescale or the unity, then this operator is given by there is a fixed set of diagrams which dominates, and that's the Markovian limit, and that you understand very well. But not only that, you also, of course, have the correction, the noise. So the full dynamics, which you write as the T plus B. So the B is given also the Dyson expansion, but you don't take any traces here, so it has a similar expansion. And then you can, of course, study the noise correlation functions, which are given by similar traces of various Dyson expansions here. But in the end of the day, when you do that, they inherit whatever the correlation of the original environment was. And the noise correlation functions will have the same decay. So again, inverse powers of the times. So you have a random walk in a random environment where the environment correlations decay in time like integrably. That's a simple dimensional analysis, and you see that this should be diffusive in dimension 3 and more. Okay? And indeed, that's what happens. So once you run this renormalization group, you are getting successively compute this effective scale L to the n correlations. And what happens is that they preserve their decay in time exactly in the same way as the original noise was. And the only thing which is changing is that their amplitude goes down as n goes to infinity. So the noise correlation functions go to 0. So that means that once you have that, then the noise eventually drops out, and you have just Markovian evolution, and you have the diffusion. Now, so that's the end of the story in this case. There are some other things which you can do with this. If you take infinitely massive particle, then you have the problem of studying a confined particle interacting with a radiation field. So with Wojtek we did. It's sort of instructive to do this model also from the point of view of statistical mechanics. So the previous model where you had the diffusive motion has scale invariance, and it required this multi-scale analysis. You have slow decays of correlations. This is a standard problem of high temperature expansions in statistical mechanics. So if you couple this confined particle to a thermal reservoir, then what you expect it is to thermalize, of course, and indeed that's what you can show here in this model. And when you go to 0 temperature, namely look at just the ground state, then again you can study the dynamics, and what we proved here was what we'd call not return to equilibrium and return to ground state. So in long times you go to ground state and you have asymptotic completeness in the sense that every excited state relaxes to ground state by spitting out photons which disappear to infinity. All of this you can do without the renormalization group, because here there's no need anymore to go to longer scales. It's just ordinary high temperature expansion of statistical mechanics. So it's slightly amusing alternative approach to these problems which people have been studying by different means in the past. Okay, so let me with the few minutes I have, let me go to these extended systems. So what we show, so I showed you this. We had this class of models for the Brownian motion, so particle interacting with the environment, where one could show diffusion or attempt to show diffusion for weak interaction with the environment. So there was this picture that at least there is a time scale, this kinetic time scale, so that in the kinetic scaling you get diffusive motion. And then the question whether the full thing is diffusive or not depends on some renormalization group properties of the effective motion in that time scale. But nevertheless, at least there is this kinetic time scale which you can take as a starting point of your analysis. So there are a couple of other models in the if you go back to the bigger problem of studying an extended system and showing energy diffusion or something like that, Fourier law. Of course, there is sort of one model which people have studied a lot, where you look at a lattice system where you have oscillators. So you put at each lattice point oscillator, so the momentum, and then you put some anharmonic oscillators, so lambda times Q4 is here an example. And then then the oscillators are talking to each other, so there is a nearest neighbor coupling. So if you wish classical Hamiltonian of a classical phi 4 theory.
Zero match.
I'm sorry?
But zero match. You see classical phi 4, but it's zero match. Free particle has zero match.
Yeah, I could put, yeah, it wouldn't change much actually here. I could put here also m squared times q squared.
I would have thought this was hot. So.
Well, okay, I mean, on the level I'm discussing here, this is impressionistic. So let me, actually, you expect just with this, the mass, for what I'm saying, this is what you expect. That once this lambda is non-zero, then you have diffusion and Fourier law. Mass plays no role in that. Okay, so again, if you look at time evolution, so now you look at the Hamiltonian evolution with this Hamiltonian, then it formally again has a Markovian limit as lambda goes to 0. And you do exactly the same scaling as in an Anderson model in all these cases.
You're looking at classical time evolution, right?
You look at, let me try to explain slowly what it means. So what does it mean? I have this, you put it in a finite box and then take the box to infinity, but you have a big system, so lots of oscillators, and you look at the evolution, time evolution with this classical time evolution with this Hamiltonian. Okay? So you start with some initial state, and I'm describing you the weak coupling limit, the Markovian limit as lambda goes to 0. So let me take as my initial condition some Gaussian measure in the positions and momenta. Okay? That's the stationary measure when lambda is 0, is Gaussian. Okay? For instance, the Gibbs measure would be an example. So let me take a Gaussian measure with covariance. Let me call the covariance G0. 0 means time 0. And now the statement is that now what you do, you go take that measure. Let me call phi t the Hamiltonian flow and measures. So I go in time tau over lambda squared like always I've been doing during this talk. And then I scale it diffusively like we did, kinetically. So take spatial scaling by 1 over lambda squared. So that's a new measure. In general, of course, since lambda is non-zero, it's non-Gaussian. But the statement of the weak coupling limit is that now I keep the tau fixed and take lambda to 0. The limit is a Gaussian measure with some covariance g tau. And this g tau satisfies a closed equation which is diffusive with diffusion constant 1 over lambda squared. So there's a, if you wish, a Boltzmann type equation, kinetic equation for the g tau. And once you study, so g tau gives correlation functions of positions and momenta. And then this has a diffusive limit as the tau here goes to infinity. This is not proven, so I put here these names, but none of this is proven. So you can heuristically derive this equation. So Herbert calls it the Phonon-Boltzmann equation, and with Jean Bricmont we did a little bit sort of nonlinear Boltzmann equation analysis of that case also. Now, in that way, this is very analogous to the problem of Rayleigh and Anderson models. So it's very similar phenomenology, and actually, if you replace this thing here by q squared and put a random mass there, then it's exactly the problem of kinetic limit of the Schrödinger equation, because the linear Hamiltonian dynamics, of course, can be written in a Schrödinger type dynamics, and the random mass then produces a random potential type thing. So Lukarin and Spohn showed actually the kinetic limit in that model. In this nonlinear model, it's actually not proven. It's probably not that easy even to do the kinetic limit here. Not to mention then to go beyond the kinetic limit. Okay, there's another class of problems which resembles the one which I described to you, where we could prove diffusion. Namely, what was that model like? That was a model where we had this spin. What was the function of the spin really? This environment was interacting. The particle was moving very slowly, but the spin was thermalizing. So the spin was providing some sort of randomness, of course, deterministic randomness, which then started to kick the particle randomly, and it diffused. Okay, so our model really looked like a random walking random environment because of this fastly thermalizing spin. So you could try to do the same thing in this Hamiltonian system. Think about a big system consisting of small parts, and you couple the parts together, but each of the small parts has a very fast dynamics which thermalizes quickly. So chaotic dynamics which thermalizes the dynamics, the state of the part of the small part, and then they interact together every now and then, and the interaction then looks like a random kick. Okay, so here is a model. So you take Hamilton at each lattice site. You take a Hamiltonian chaotic system, for instance, a billiard or an Oslo system. So at each lattice site, you take a chaotic system, and then you weakly couple them by something. Okay, so nearest neighbors, for instance. Now there is a Markovian limit, exactly like in my simple spin particle case. You scale only the time, not the space. And look at the energies of the systems at each site x. Okay, look at the energies of them. Then what happens is that these energies have a limit. This process. This is of course a deterministic system. I mean, this flow deterministically with the time. But once I take the limit as lambda goes to 0 and time going to infinity like that, they converge to the energies. This is not expectation, this is energy. They converge to a diffusion process. That was actually proven by Dolgobiat and Liverani. So instead of here, where even the weak coupling limit is sort of seems to be quite difficult to show, here you can actually get the diffusion process. Plus half of the nearest neighbor, the interaction energies, for instance. So write the total energy as sum over x, E of x. So it's this, and say distribute those pieces. Okay.
So what do you have? You have a chain of chaotic.
Take chain for instance, and then I take half of the from the left and the right. So the sum of those is.
But each element of the chain has
Each element of the chain has internal chaotic dynamics.
But then they're coupled, that's the H1 coupling.
And then they are coupled weakly. Yeah. So what happens is that most of the time they just chaotically thermalize themselves, and then every now and then they exchange energy. So it's exactly like my spin model. And indeed, that's what happens then. The limit is a diffusion process. So so the energy will be diffused. Yeah. Yes. But of course, that's in the kinetic limit, in the weak coupling limit. Weak coupling limit. But here you could imagine doing exactly what I was now doing in the case of the spin, namely fixing lambda, taking, looking at the dynamics at not infinite lambda going to 0, but fixed lambda, taking the kinetic, this diffusion process as the starting point, and then doing the random environment around that. Okay, that's still not so easy in the Hamiltonian system, because in the Hamiltonian system you can have all kinds of crazy things. So if you think about this, say couple billiards, the billiard could by some bad luck just stop moving, one of them, and then you wouldn't have any transfer energy. So in Hamiltonian system, the energy conservation and piling up could happen, and that could be difficult.
So the chaotic sites, do they have chaotic layers that are constantly both sides, or are they completely chaotic? Or
Here I'm thinking of a completely chaotic. So take for instance billiards which are moving on their tables, and then coupled by springs to nearby billiards, but very weakly.
so energy fluctuations cannot destabilize the chaos.
They don't destabilize the chaos. Yes, exactly. The coupling is very weak, so it doesn't destabilize.
This system, which governed by H naught, is not chaotic because there are zero directions.
There are what?
Zero directions.
Yes, there is the energy, of course. There's the conserved energy, and the conserved energy is the one which is the only thing which is the energy is conserved in the and what happens is then that you exchange these energies, but in a random way. So it's exactly the similar situation as in the spin model. In the case where I don't look at the I should stop actually. The Hamiltonian system, but I look at coupled maps. So coupled chaotic maps with Jean Bricmont, we actually, with enough assumptions for these maps, we were able to prove something like this. Okay, but
With or without the scaling limit?
without the scaling limit. Without the scaling, just along the same lines as I was describing you. So writing it as a random walk in a random environment and showing that the noise goes to 0. But for the Hamiltonian system, there are lots of obstacles in doing that, because in Hamiltonian system you can have sort of anomalous cases where energies pile up or deplete. And we made a system where this doesn't happen. It's not a Hamiltonian system, so we're cheating there, and that's certainly not something which is giving anything for the Hamiltonian system. But anyway, this is sort of a system which is not that far from being realistically approachable. So let me just conclude that in a very modest way, let's just say that it's not completely excluded that one could proceed along these lines in the Anderson model, because what we really did was we took the Dyson expansion, went to the kinetic scale, wrote it as a average plus noise, and then started to go scale by scale. We could exactly try to do the same thing for Anderson model, and I suppose if you were careful enough, you might be able to show how this noise, once you take also always the average to the annealed part, how this noise actually goes to 0. You would expect that to happen, but it's a different matter of how actually to prove it. Okay, thank you.